Okay, let us revisit the whole construction. So we are defining a fully connected feed-forward artificial neural network. It consists of L layers. Among them, we have the input layer, the output layer, and L-2 hidden layers. Now, it is called fully connected because every unit or every neuron in layer L is connected to every neuron or every layer in layer L-1 and in layer L+1. But of course, hypothetically, you could imagine networks that are not fully connected. So something that say every unit here is only connected to, I don't know, 2 or 3 units, like this, this, maybe 3, maybe this to 3, maybe this to 3, and this to 2, something like this. And maybe for some types of problems, this would be better. Right? But now I'm not really going to get into detail here. So we will work with just fully connected neural network. So feed forward is because basically when we give it some input, right? So it is going to just process it layer by layer, and then it's going to first apply the second layer, then third layer, and so on. And then finally, we're going to apply the output layer and compute the output. And so this is how it works. There are more complex architectures when it's not just like from left to right, but there are so-called recurrent neural networks when we so in the process of computation, so every time we are kind of using the new input plus we are reusing some of the old input. But in any case, in this lecture, I'm going to just talk about fully connected feed-forward artificial neural networks. So each unit in layer L has some weights, one bias, and an activation function. Now, the number of weights in each unit is the same as the number of units in the previous layer. Right? So because if we have if we have some layer L-1, right? So we have, say, I don't know, 4 units here, then these four units, they become the input of layer L, right? Which means that each unit in layer L, it needs these 5, right? So 1, 2, 3, 4, 5 is going to need 5 weights. So here K is going to be 5. Okay, and then together, so all units in layer L, if we look at the biases for all units in layer L, then together they're going to form a bias vector. And if we look at all weights in layer L, then together they're going to form a matrix of weights. So, and later, in order to process the input of layer L, we're going to take the output of layer L-1, multiply with the weight matrix, and add the bias vector. And then all parameters together, so the collection of all parameters together, I'm going to denote it by theta capital. So this is the Greek letter theta, and it's going to be just all biases and all weights together. Right, so activation function, theoretically, each layer can have its own activation. Well, theoretically, even every unit can have its own activation function. But in practice, this is not possible to implement. I mean, at least so we're going to work with this library called Keras. It is a very popular library. It exists for R and Python. Well, Keras does not really have the possibility of using different activation functions for different units within the same layer. So it's always the same activation function for everything in layer. But layer 2 and layer 3 and layer 5, hypothetically, they could have different activation functions. But in practice, we just use the rectifier. The output layer, the choice for the output, the choice of activation for the output layer, it depends on the machine learning problem. So we are using sigmoid for binary classification, and we are using the identity function, or we can call it a linear activation for regression. Okay, so now please do a little quiz on fully connected neural networks.